So limits is something that you see in calculus. So the first thing that you generally do when you get to calculus is find the limits of functions. So we're basically giving you a week of calculus so you have some idea of what you're going to get into and you have some familiarity with the concept. So we've actually done limits in college algebra, or just in algebra in general when you talk about end behavior of a polynomial and asymptotes, but we don't call it as such because we're not using limit notation. So basically, a limit is you're asking yourself a question. You're saying, I've got this x value. As I approach this x value on my graph, either from the left or the right or for both sides, as I'm getting nearer to this x value, what is happening to my y? What is actually happening in my graph? What y value am I going to? Like it's almost the same as finding the y value at that x, but not exactly, because sometimes there are cases like where you have an asymptote where if you have an asymptote of x equals 2, there's no x value at 2. But you can still find a limit. You can still see, well, if I were to have a point there, what would it be, basically? So you're following a pattern, and so you find limits of things when the value doesn't exist, basically, to kind of fill in the gap, so to speak. So when we're finding limits, we have specific notation, and I've got 3 examples here. So we use a lim, and this is actually in Microsoft Word. It's one of the options that you have. Actually, let me open up Word to show you guys where that is, because I know a lot of you, it's not required to type, but a lot of people do choose to type. So let me show you where that notation is. So when you go to inserts and equation, the limit part is under this limit and log right here. And so this is what you're going to want right here is the limit. So we have a limit, and in this box is the function, basically. If you're looking at a specific graph, whatever your function is. So let's say my function is x squared. So you would type in x squared, and so that's the function you're taking the limit of. That's the graph you're looking at. Underneath the limit symbol, this is what you're saying. This is where you indicate what x value you're interested in. And so you always have x here, and then you always have an arrow. And there are 2 ways you can do the arrow. You can, this drop down right here where it says more. You can see that there's some arrows here, but you can also go to the basic math and do letter arrows right here. And then you can pick the particular arrow that you want. There's actually a shortcut when you're typing. If you hit the hyphen and then you hit the greater than symbol to basically make the shape of an arrow. See, that's what it would look like if you type that. It automatically converts it to an arrow. So that's just saying as x approaches or x nears this x value. So if I wanted to know what my y value is when x heads towards 4, this is what I would write. And that's how you indicate the limit. So that's the limit notation. And when we say that we're heading towards 4, we're assuming that we're looking at the left side and the right side. We want to say if I go from the left on my graph and I head towards 4, or if I'm going from right to left and I'm heading from the right, moving the opposite direction. Sometimes we have limits where you're only interested in one side, like you're only interested is where it goes when you head from the left to the right or from the right to the left. So when you're heading from the left to the right, you're starting in the negative side. So what we do is we indicate that with like an exponent. So you can hit your exponent button and you put a minus sign there. And so it'll put a minus up there, and that just indicates that we're looking at just the left side, coming from the negative side of the graph, like the negative x values. You can also do the positive side, and so there you just put a plus. So it's an exponent, you just put a plus, and that tells you from the left side or the right side. So this is limit notation, And so I've got that here just written. So you basically plug in a number where I have the number symbol, and then you would have a number where it's equal to, and that would be your answer. So this will make much more sense if we look at graphs and we look at actual functions. So I just have tons of examples here. Find the limit of f of x equals 2x plus 5 as x approaches -1. So I'm going to start by actually drawing a graph, because this is where it sort of makes sense graphically. So it doesn't have to be perfect, but I know this is an equation of a line, and it's in slope-intercept form. So I know that my y-intercept is at 5, and then my slope is 2/1, so I'm going up 2/1. So that means at 7, I'll have a point right here. And so I just have a sketch of my line. So we want to know what is the limit as x goes to -1. So we should find out what -1 is, what that y value is. So I'll plug that into the graph, or I mean, you can use Desmos to graph, but I'm going to just do this by hand. So that's -2 plus 5, and that's at 3. So we'll say that's about there at -1. So we've got our graph, and we are interested in what happens as I approach this, I should say this magical value, the x value. We want to know what happens to y as I'm getting nearer -1. So I'm going to first write, oops, that's the highlighter. I'm going to write the limit notation. So to indicate this, we write lim, and then underneath it, we're indicating that x is approaching -1. And then you put your function 2x plus 5. You don't have to put that in parentheses, but that could make it easier to read. And then equals, and then that's going to be what our answer is. So I'm going to just try to color code this as best as I can. So we're going to look at both sides. So I'm saying as x is, let's say I'm moving from left to right, and my x value is going towards -1. My y value is approaching this value right here, which is 3. Our graph is getting closer and closer to a y value of 3. And then we also want to look at what happens if you're going from the other direction. So if I'm going from right to left, as my x gets closer to -1, my graph is getting smaller and smaller and smaller, and it's basically heading towards this value. On both sides, the y value is getting closer to 3, and in fact, it is exactly 3. So we would say the limit is equal to 3. It's basically as x goes to -1, where does y head? Y heads to the value 3. Now, a situation like this is silly because you can just plug in -1 and you get a value of 3, and you don't have to think about this as a limit. But limits get useful when there is not a number to plug in. So I'm going to take a look at this. So here we have a quadratic. So this is going to graph a parabola. We have -x² plus 2x plus 8. So this is where it's actually going to come in handy to have a limit. So first, my y-intercept is at 8. And let's see. So if I want to sketch this graph, I'm going to factor. So first I'm going to factor out a -1. That's x² minus 2x minus 8. And then if I factor this, that is x minus 4, x plus 2, I can find my x-intercept. So I'm going to have an x-intercept at 4 and then at -2. So halfway to before -2 would be at 3. Let's see. So that's 2, 4, 5, 6. So at 3 would be about the halfway point. So I'm just going to kind of sketch my graph, so it's going to look something like this. So we've got our parabola. So we're going to look at the limit from two different positions. We're basically going to say, okay, as x goes to 1. So we're interested in what happens when we near an x value of 1. So we're looking for what is this y value basically. As we get near, what is this value? As we go from the left and right. So as our graph is going from this side and this side, of what y value are we going towards? So we can find that by actually plugging in 1. So that gives us -1 plus 2 plus 8, and that's equal to 9. So we'd say that the limit as x approaches 1 of -x squared plus 2x plus 8 is equal to 9. That's the y value when you get near to 1, or when you're at 1, the y value is 9. So again, that's not really useful because we can read that off of the graph. What is useful is when we're interested at what happens at things we can't graph, like infinity. We cannot plug infinity into an equation. That's not an actual number to plug in. So you can't just say, okay, let me plug infinity in and try to do some math, because how do you square infinity? How do you multiply infinity by 2? You can't do that. So this is where you have to do a limit, because this is the only way to determine an answer. And so then you have to basically find the pattern or what's going on. So as x approaches infinity, what we're looking at here, and I'm going to do this one in blue, we're saying as my x value goes further and further to the right, so as I'm heading to the right here, as I'm getting larger and larger x values, what is happening to my y value? So our graph, the y value is going down, and this pattern, this arrow says that it's going down and down and down. So it's getting more and more and more and more negative. So if you continue the pattern, if your x goes on forever, your y here is going to go down forever. So it's going to hit negative infinity. So it doesn't actually hit like a number. So our limit as x approaches infinity of this equation, -x squared plus x plus 8, or this function, is equal to negative infinity. This is basically saying if I was to keep going on forever plugging in x values and they get bigger and bigger and bigger, my y value is going to get smaller and smaller and smaller, and it's basically going to approach negative infinity. It just goes down forever. So that's where the limit comes in handy, because you can't actually plug in infinity and somehow get negative infinity out. You can't plug in those numbers, but you can look at the pattern and kind of see what's happening to the graph to determine where it would go. Are there any questions? Okay. So this is a polynomial. You know, this is a polynomial. Polynomials, when we're asking about where things go when we approach infinity, what we're asking for is the end behavior. So this is where it connects back to algebra, where you talked about end behavior. So when you have a polynomial, we found the end behavior basically using the leading coefficient test, where you look at that first, the highest term with the highest exponent and the number, the coefficient, and that told you what things would look like basically at infinity. Whether it was positive infinity or negative infinity would tell you where the graph would go. And that's what end behavior is. So if you have, and it depended on your degree. If you have a quadratic, that's an even degree, and so it's either going to go up on both ends, which means it's going towards positive infinity, or it's going to go down on both ends. And then like with the odd term, like a cubic, it goes in opposite directions. So if you think of that as I'm finding the limit, as the end behavior is what happens when my graph goes on forever towards infinity or negative infinity, you are finding limits. And so you're basically looking at the limit as x goes to positive infinity or x goes to negative infinity. And so you're looking at the end behavior. And so that is basically saying what happens to y. Where is y going? If you have a positive leading coefficient, it opens up. So that means your y values are going to go up to positive infinity. They're going to keep getting larger. But if it's a negative coefficient, it's going down. It's going to go down forever towards negative infinity. When end behavior is taught in algebra, they usually write something like as x goes to infinity, y goes to like infinity. They usually write it that way. But now we're introducing new notation. So instead of using that notation, you're going to use something called the limit. And we have a different way of writing it, but it means the same thing. It's just saying, okay, as I go follow this part for x, what happens to y? So when you have odd powers, then they're flip-flopping, sort of like you're not going to have the same answer going to negative infinity and positive infinity. It depends on what your shape is. So if you ever have a function and you're like, hey, this is a polynomial and it's asking me for the limit as I go to infinity or negative infinity, all you have to do is think about the end behavior. You don't have to graph it. You can use your leading coefficient test to find the answer. So you don't have to do any solving. You just have to recognize that it's a polynomial and what the general shape is going to be. So that's why in algebra we focus on what are the shapes of all these things, you know, the parent functions, knowing what they look like, because that way you don't have to do any calculations. You can find a limit towards infinity or negative infinity simply by knowing what it's supposed to look like. Are there any questions? Okay. So let's take a look at something different. Here we have a rational function. So we're out of the polynomials. We have something more complicated. We have 3x plus 1 over, and then x plus 2 squared. So I'm going to actually start pulling up decimals for these because I could graph this by hand, find the asymptotes and stuff. But it'll be a lot easier if I just use decimals. So I'm going to try to have that up here. So I'm going to type in our function f of x equals 3x plus 1 over x plus 2 squared. Okay, so now I'm going to zoom out here so I can get a good picture as well. So this is what it looks like. So our first thing says as x approaches 0. So we're saying, okay, when x is coming close to 0, what is happening to y? So you can see as x is going towards 0, from either side, there's an actual value it hits. No, that's not 0. That is y equals 0, x equals 0 right here. So as x is approaching 0, as our x is going towards the origin, there is a y value, and it is essentially the y-intercept of 0.25 or 1/4 here. So our limit as x approaches 0 is it's just following the graph, and it's just, okay, that's that value. Plug it in, that's what you get. So oops, make sure that I write this down. So we've got the limit as x goes to 0 of 3x plus 1 over x plus 2 squared. Nope, 1/4. Because that's literally the y value at x equals 0. Is it's equal to 1/4. Next is as x approaches infinity. So we're going to have to zoom out here. And we're saying as our x values get bigger and bigger and bigger, and you can see that the graph is basically looking like it's hugging the x-axis here. And if you remember anything about rational functions, that is the horizontal asymptote, that as it heads closer and closer here. So when we're asking where x approaches at infinity, we're saying what is the horizontal asymptote, essentially. And so the horizontal asymptote of a rational function is depending on the degree. On the top here, we have something that's linear. In the denominator, we have something that's x squared. If you were to multiply that, you get an x squared. And when the degree of the top is smaller than the degree of the bottom, that's where your asymptote, your horizontal asymptote, is 0. And you can see that it does look like it's getting close to 0. And I could just keep picking smaller numbers. And you can see that the numbers are getting closer and closer to 0. So our limit as x approaches infinity is 0, because the y values are getting closer and closer to 0. So you're going to want to be really good at drawing the infinity symbol. And if you are typing and you want to know where is this infinity symbol here, if I was to type infinity, let's see if I remember where it is. It might be under basic math. Yeah. Sometimes it's hard. Yeah, it's right there. That's our basic math. I usually do the shortcut. So if you hover over it, it tells you what to type in. And so I usually just learn these shortcuts, and then it will convert it for you. So there is a symbol for infinity, and so you can use that when you type that in. So our limit as x heads towards positive infinity here is 0. So that's where the y value is going, and that is actually the horizontal asymptote. So now the last one is what happens when x approaches -2. So I'm going to move back and I'm going to have to zoom in here. Okay, so x approaches -2. You can see that that is where we have a vertical asymptote, and that actually comes from the denominator. If you plug -2 into your equation, you get f of x equals undefined. So you can't actually get a number there, because when you plug it in, you get undefined. So if I was to write this out, f of -2, I plugged it in. So we get -6 plus 1, that's -5 over 0 squared. You get undefined, because you can't divide by 0. Now, undefined is not the answer to the limit, because that's not really something that you can have. So this is where a limit is handy, because the value is undefined. You can't actually plug -2 in, but if you follow the pattern, you can see that your graph is going more and more negative as you get towards -2. I can even put a line there to help. So you can see that as we get closer and closer to x equals -2, our graph is basically, our y values are going down and down and down. So they're actually approaching -infinity. So our limit is x approaches -2, the 3x plus 1 over x plus 2 or x plus 2 squared is equal to -infinity. And this is a location of the vertical asymptote. So if I were to plug in -2, I don't get an answer, I get undefined. But using the limit, you can still get an idea of what the graph looks like. Because if you were just trying to plug in numbers, undefined wouldn't tell you anything. It wouldn't tell you what the graph looks like. But knowing it's going to -infinity, then you know that either side of that, that's got to have an asymptote, and the numbers are going to get smaller and smaller. Are there any questions? Okay. So let's recap information about asymptotes in case you don't remember. So rational functions have horizontal asymptotes, vertical asymptotes, and then there's also called the oblique asymptote, which is also a slanted asymptote. And it is entirely possible for a limit to approach an equation. So that is possible. That makes more sense when you really get into calculus and you start doing derivatives and you find limits of things and they actually end up being equations. Now, everything we're going to deal with, our limits are going to either approach infinity, -infinity, or numbers, basically. So this is just a recap of what these asymptotes mean. And so that's just, you know, there for your reference. But basically, here's the different possible shapes that you can have. These are the general shapes for rational functions. Because if you have a limit and it's asking for positive or negative infinity, it's asking for those horizontal asymptotes. And so knowing how to find those, what the general shape is, that helps you. And then if you're approaching a vertical asymptote, you have to know also the general shape. So let's take these two cases. So this is where things get interesting. So let's look at the shape on the left. So you've got a horizontal asymptote, a b, wherever that is. And so if you're looking for the limit, if you're going towards infinity or -infinity, you can find that value. It's going to be whatever that asymptote is at b. The vertical asymptote here, we have to look at it from the left side or the right side. Because if I was just asking for what happens as I approach this vertical asymptote, there's two different answers depending on what side you're looking at. If you're looking at the left side, it's going to -infinity. If you're looking on the right side, it's going to +infinity. So this is where you want to use a one-sided limit because they don't match and there's two different answers. So the left side is indicated with this negative right here, and the positive is indicated with the right side of it is indicated with a plus. Now the graph on the right, you don't have to do a left side or a right side because it's the same, they approach the same thing at the asymptote no matter which side you're looking at. They both go up to +infinity. And then this is basically just the same thing, it just flip-flopped. These are if you have like a negative coefficient. If they're going in opposite directions, you have a left side and a right side limit. Otherwise, you can have it from both sides. So let's take a look at another graph here. For x minus 3 divided by x plus 1. Okay. So I'm going to have to reset my graph. Okay. So here we are. And our first one is what happens as x approaches 0. So it's approaching the origin. And you can see that there's actually a value. As x is getting closer to 0, we actually have a number at -3. So our limit is -3. If you plugged in 0, that's what you would get. So it heads towards -3 on either side, and in fact is -3. So the limit as x goes to 0 of 4x minus 3 over x plus 1 is equal to -3. We can see that on the graph. Next, x approaches positive infinity. So we're looking for the horizontal asymptote here because it's a rational function. And so you can see on the graph that it looks to be getting close to 4. And you can actually find that from the equation. So we're looking at the horizontal asymptote, and we're looking at as we go to the positive values, and it almost looks like it looks exactly at y equals 4 here. So as x goes to infinity, our graph is approaching 4. So the limit as x goes to infinity of 4x minus 3 over x plus 1 is equal to 4. So now let's look like as x goes to -1, and that's going to be our vertical asymptote because -1 in the denominator makes it undefined. So this is where we have it going in two different directions. If I'm heading towards -1 and I'm coming from the negative side, so I'm going left to right, my graph is going up to positive infinity. However, if I'm coming from the right side, heading from the positive side, and I'm going to -1, my graph is going down to negative infinity. So they're going in two different directions. If your question is asking about it approaching a number and does not specify whether it's a left side or a right side, you have to assume it wants both sides. And in this case, because both sides don't match, they're going in opposite directions, this is what we call the limit that does not exist. Oops. Oh, too far. So we have the limit as x goes to -1 of 4x minus 3 over x plus 1. And what you write is d and e. So I'm going to just put a note here that the one above is the horizontal asymptote. Left side went to positive infinity. They're coming from the right side. Comes from negative infinity. They don't match. And so if it's not specified a specific direction, you assume both sides and they need to match in order to have a limit. Since there's a contradiction, we say D and E does not exist. So this is just recapping. If both sides don't match, it's D and E. Now, this is a very common thing, is I see a lot of people just write undefined. That is not the same thing. Limits are never undefined. There is always a limit. So there's always an actual limit that you can have, except for if it does not exist. But I mean, it's not going to be undefined. So you don't want to write undefined, and you also don't want to write infinity or negative infinity because those are not the same thing. You have to write D and E for does not exist. That's the specific terminology here. So even if a limit at a specific point does not exist, you can have limits of either a left side or a right side because you're only looking at one half. So you'll only look at one part of it. So you do have limits from one side, but you may not have a limit from both sides. So it may not exist looking at it together, but if you're just looking at one side of the graph, it can. Are there any questions? Okay. So here we have a piecewise function. And so I'm actually going to also graph this one. So if you've ever wondered how to graph piecewise functions in Desmos, you're now going to find out. So I can do x minus 1, and then this is for x less than 0. And so it only graphs for x less than 0. And then I have x squared, and this is for x greater than or equal to 0. If you hit the equal sign, it will change symbols. And so now we've got our piecewise. We have two different pieces here. So as x approaches 0, so as you're heading to 0, you can see at 0, we don't line up. One side has a y value of 0. The other side has a y value of -1. So these don't line up. So because it does not match on either side, our limit as x approaches 0 does not exist. So there's a gap there and it doesn't match. I'm going to just write this up here rather than recopying my limit notation. And for something like this, because it's a piecewise and it's hard to write, say we're approaching 0, you could just put f of x. So we could write that. You don't have to put the whole piecewise thing there. As x goes to infinity, so here I'm only interested in the right side, so I'm going to just kind of scroll up, and you can see the right side is a polynomial, so that's talking about the end behavior, and that is heading up towards positive infinity. Oops. So the limit as x goes to infinity of f of x is infinity. Then we've got as x approaches -1. So I'm going to zoom in here. And if that is an actual value on the graph, then all you care about is what is that actual value at -1, which is -2. So as x approaches -1, our y value approaches -2 because it's actually existing on the graph. So our limit as x goes to -2 of f of x, -1 of f of x equals -2. Now here's another piecewise, and this one has what we call a hole, and then there's another value underneath it. So this one is, I did want to, the graphing of this one was a little difficult for me to figure out, so that's why I just included the graph here. So if we want to find the limit here, as x approaches 0, so we're saying, okay, where is y heading? As we're getting towards an x value of 0, and that is 0, according to our graph here. So again, it's a piecewise. I'm not going to write the function. I'm going to just write f of x. So as x goes to 0, our y value is going to 0. Next is as the limit as x approaches infinity. So that would be our graph is going higher and higher and higher. So that is also approaching infinity. Now this is where people mess up, is when x approaches 5. So when x approaches 5, from either side, it is approaching this value, 5, the y value of 5. So that is what the limit is. The limit as x approaches an x value of 5 is equal to a y value of 5. Even though the y value at 5 is equal to 3, if you follow the shape of the graph isn't going there. The graph appears to be going towards 5. So that is what the limit is. So the limit sometimes is not the same as the function value if you have holes, or in this case, this is called a discontinuity. So x equals 5 is a discontinuity. And you want to pay attention to where the graph is going, not the actual value at 5. So you're following the graph and what it looks like the pattern is. Are there any questions? Okay. And there's an example similar to this on the homework, and there's actually one with a jump like we have here as well. So now that we've looked at them from different graphs, there are 3 ways you can find limits. We've been doing the graphical approach. We've been basically looking at the graph and figuring it out from there. But you can also do it with a table of values where you plug in numbers and then you're trying to figure out what number it approaches. Or an analytic approach is where you actually use algebra or calculus and you're using equations to figure it out and you're not looking at a graph or a table of numbers. So there's examples of these on the homework. So I'm going to start with the table of values. So we want to find the limit as x goes to 0 of sine of x over x minus 3. So when we're finding the limit as x goes to 0, we want to look from the left side and the right side. So what you want to do is first, if you're going to have a table of values, 1, 2, 3, 4, 5, 6, I got 7 values. I want to put 0 in the middle. Just to see first what happens if you plug in 0. Our f of x value here is what you're taking the limit of. So f of x is equal to the sine of x over x minus 3. So I'm going to fill in the table, and I'm going to just start with 0, because often there's a point there, we can actually calculate that out. So this is the sine of 0 over 0 minus 3. Now here's the thing. You need to use radian mode when you have this. I see a lot of people make mistakes because their calculator is in the wrong mode. So whenever you have an equation, you assume it's in radians unless told otherwise. So you need to make sure your calculator's in radian mode when you plug in the numbers, or you're going to get the wrong table. So sine of 0 is 0. So that's 0 divided by negative 3, so that is 0. So you would think, okay, the limit should be 0, but we should verify by picking numbers on either side. Because as you saw here, the actual function value didn't match if you looked from left to right. So you have to make sure the pattern holds as well. So what I usually do is I like to have 3 decimal places. And I want to plug in a negative and a positive. I want to plug in basically numbers on either side, but really close to 0. So if it's centered at 0, I'll have a negative and a positive. Sometimes we're not centered at 0, and then you have to kind of figure out a good number on the left, a good number on the right. And I'm going to plug in an x value of negative 0.001 into my equation. And so this is actually, I'm going to pull up Desmos for this to save some time. Because Desmos is really nice. So I'm going to just plug in f of x, or type in our f of x. And even though we're doing with a table, I'm not going to actually look at the graph. I'm just going to care about the values here. Make sure you have your parentheses so that you have your sine of x by itself. It's not x divided by x. It's the sine of x divided by x minus 3. And so if I want to know a negative 0.001, Why is that not? Oh, it doesn't like that I have x multiple places. Okay, so I'll delete all these. There we go. Okay, so we get this decimal value. And so I'm going to, that's negative 0.00033. How many is there? 0.00033. The right number of zeros. So that looks like we're close to 0. So that looks like, okay, this would make sense that it approaches 0. And then let's do the positive side. And so that looks like it's not quite the same number. If you notice that it's not the same number, it does not form a mirror image, but it rounds to the same number. We've got 3 negative, 3 zeros, and then a 3, 3. Oops, it keeps turning off my pen. So this would apply, okay, it does look like the pattern matches. We're getting close to 0. Those values are close to 0. So the limit should be 0, but we should just double check that it doesn't do anything funky. And so then I usually remove a 0 and check those numbers. So I'm going to, and because my Desmos already has the positive version, I'm going to just remove a 0. Okay, so that removed a 0 here. We have negative 0.0033. Which is still close to 0. And then I'm going to plug in the negative version. Ah, this is interesting. We get a positive 0.0033. So you can't assume that it's a mirror image. You can see in this case it's not a mirror image. And then for good measure, we'll again remove a 0 and check negative 0.1 and 0.1. So that's positive 0.03. And then when I remove my negative and plug in a 0.1, that's negative 0.03 roughly. And so when you estimate the limit, think about this if you were graphing it. We're close to 0. So I'm at 0, I'm at 0, and then I'm a little negative, and then I'm, oops, a little negative, and then I'm getting more positive. At 0, and I'm negative, and negative, and then I get more positive. You can see that as we approach 0, we're actually approaching 0. So when we approach the x value of 0, our y value is also getting to 0. So estimating the limit is more than just filling in the table. You need to actually write the limit of x goes to 0, sine of x over x minus 3 is equal to 0. So you need to actually state what the limit is so that you're actually estimating. So if you fill in the table and you do nothing else, you've not actually found the limit. Now, table of values are used for limits that are possibly hard to tell in a graph, or ones that you can't do algebraically. Now, there's no way you can kind of solve or find a limit. When you get to calculus, you'll find all the different methods that you can for finding it algebraically. But a table of values is used for weird things like you have trig functions, or you have e to the x, or natural logs, or things like that. That's usually where you use a table of values. Are there any questions? Okay. So here we're going to estimate the limit. It's the same function, but it's going to be at x equals 3. So the more important thing here is just setting up our table, picking our table of values. I usually basically take whatever I had here if it was centered at 0 and I add those to my values. So if I was finding the limit to 3, I'd add 3 to each of these and get my new table. So that means I would check 3.001, 3.01, 3.1. And then if you go in the other direction and you have like negative 0.001 and you add 3, that gives you 2.999. And then if you follow the pattern, 2.99 and 2.9. So if your value, if you're not at 0, if you're somewhere else, even if you're in negative, you can do the same thing. You just add those to this base table here, add your value, and then that can give you your new table. So I'm going to show you how you can use Desmos to even, rather than having to plug everything in here, you can actually use a table. So if you go to plus, you can go to table, and you can do f of, you can delete this y1 thing and say f of x underscore 1. It will use the f that you've defined, and then it'll plug in whatever your x values here. So I can put it in my values. You can see at 3, it's undefined. So our limit is not undefined. That's why we have to make this table. 3.01, 3.1. Okay. And then you want to follow the numbers. So we're negative, 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 and we're getting more and more and more negative. And then suddenly we're going to the positives. So, oops. That was not what I wanted to do. How do I undo that? There we go. Just wanted to move it not quite all the way over. So we're getting more and more negative if you're going from the left. But then if you're going to the right, you can see as you get closer, it's going more and more positive. So this is an indication that neither side matches. When you plug in numbers, they don't match. The left side's going negative, this right side's positive. So our limit here does not exist. And you can see that from the table of values because it suddenly switches signs. If it was getting closer to 0 and then switching signs, then you could say the limit is 0. But here they switch signs, but they're not even close to 0. It's getting smaller and then suddenly jumped and got big. So the limit here does not exist based off of these table of values. Are there any questions? I know that I'm nearing an hour, so I'm kind of trying to find shortcuts here. I'm running out of room. I'm going to take a screenshot. I'm going to put that on my PowerPoint so I don't have to copy everything down. Okay. So here, same thing. And what happens when x goes to -5? So again, I'm going to show you what happens, how to write the table here. So we want -5 in the center, and then you're either adding or subtracting my base at 0. So -5 plus 0.001. We get -4.999. And then it would be -4.99 and -4.9. And then in the other direction, it's -5.001, -5.01, -5.1. So that's how you'd fill in the table if it was somewhere else. It was approaching -5. So again, I'm going to use Desmos. And I can even make a new table here. and it will use x2 instead. So I can say instead of y2, f of x2, so I don't have to get rid of my other table, and then I can put in these new values. Negative 5.1, negative 5.01, negative 5.001, negative 5, negative 4.999, negative 4.99, negative 4.9. So here we're saying what happens as x approaches 5. So it seems like these numbers are kind of, you know, it's like they're getting decreasing, they're getting smaller, but there's nothing unusual. They just keep getting smaller and smaller, closer to negative 0.124 or whatever. So when you have something like this and the numbers are just kind of all in a line, then when you approximate your limit, you can approximate your limit as the actual value at negative 5. So you could say your approximate limit is negative 0.119865553. Or if you want, you can round these, and you can round to where, like if you round it to 2 decimal places, it would be negative 0.12. This would round to negative 0.12. This one rounds to negative 0.12, negative 0.12, negative 0.12. This is negative 0.12. This is negative 0.12. So if you round it enough, you can see that there's a common number they're near, and you can use that as your limit. So you can choose for your limit the exact value, or you can round it to what seems to be in common with all the points near it, if that makes any sense. Because you're estimating, you're not finding the exact value of the limit, you're estimating. So you can estimate it by what you see on the table at negative 5 or the common rounding. So I will also make sure to take a screenshot of that and put that in the PowerPoint. Okay, so I just wanted to do these two. I have 2 more. A polynomial and a rational function. So it says find the limit. As the limit goes to negative infinity, we have negative 3x squared plus 5x cubed. So this is a polynomial, so you want to be able to recognize it. So we have a polynomial, and you need to write it in standard form, or the highest power first. That's 5x cubed minus 3x squared. So this is an odd degree, so we can determine the general shape, and our leading coefficient is 5, which is positive. So if we're doing, I'll make this black. If you're using the leading coefficient test for end behavior, and the reason why we're doing this is that because we've got this polynomial and x is asking about negative infinity, this is telling us that we are looking at end behavior. If it asked for like x going to 5, I'd maybe make a table or plug in the value. But if it's asking for negative infinity, this is telling us that we've got end behavior going on. So we're going to use the leading coefficient test. So we've got a positive coefficient, it's greater than 0, and then we have an odd degree. So that tells our general shape is going to look like this. And you can go back to, I'm trying to find the slide. Here we go. This slide, which I'll have as a reference. And you can see we even have what the answers are here, basically, for the limit. But as you're going to negative infinity, it's going down. So your limit is also negative infinity. So our limit here is negative infinity. And you can find that versus end of behavior. One thing you never want to do is actually plug infinity into an equation. So never do anything like this where you're actually plugging infinity into an equation or negative infinity. We don't do that. We can't do that. So you're never going to be writing that. If you're showing the work on something like this, you're going to want to draw a picture, the graph, or you're going to want to show a table of values maybe, which doesn't really work for negative infinity. Or you can use like your leading coefficient test and then write that work. But you're never actually plugging in infinity or negative infinity. So that's not how you show work for something like this. And so I shouldn't see that. I know there's some videos where people do that, but that is not really proper calculus. It's not how we show work. You can think about it and say, well, if I plug in a really tiny value, what happens when I square it? It gets even smaller. Like, you can think about it that way, but you don't actually write it. Now here's another one. This is a rational function. And so the key here is to recognize we've got a rational function. And we're saying x is going to negative infinity. And so that is telling you if your x is going to negative infinity or positive infinity, it's asking about a horizontal asymptote. So when you're finding something like this, you're basically finding your horizontal asymptote following the techniques that you learned in algebra. So our degree at the top is linear. And it's the same as the degree of the bottom, which is also linear. And our rule was that your horizontal asymptote is basically based off of the coefficients in front of those leading terms. So we'd have negative 2 over 1. So our horizontal asymptote is negative 2. And so that's telling us that our limit here is negative 2, because it's saying what is the limit as I'm going to negative infinity. That's always the horizontal asymptote for a rational function. Now there's an alternate way to show work that is shown in one of the videos. And so if you were to show this algebraically, you start with what you have, negative 2x over x minus 1. And this is a really interesting trick, is factoring out an x from the denominator. So if I remove an x from the x, that's a 1. But if I attempt to factor x out of the minus 1, I'm left with a fraction, because factoring is you're actually dividing it out. If you've taken a class from me where I taught factoring, this is why I teach the factoring with the GCF and then the term divided by the GCF. This is actually why I teach factoring that way. It's because it's used for something like this. And actually, I'm doing bad form because I shouldn't just do equal. Every step, you have to actually write that limit part there. People forget that. I forget that. So you do have to write that limit every time. So if you look at what you have here, you have an x on the top and the bottom that cancels out. So you can cancel these x's out. And so you have the limit as x goes to negative infinity. You have negative 2 over 1 minus 1 over x. Now, any number that doesn't involve like a variable can actually be pulled out of the limit. These are some fancy tricks. So that negative 2 I can actually put in front, and then I'm looking at 1 over 1 minus 1 over x. Now this is where thinking occurs, and sometimes people write in a negative infinity, they plug it in, and you really shouldn't. So you ask yourself, okay, as my x value is getting really, really small in the denominator, it's getting more negative. What is happening to the 1 over x? So you're interested in what happens to here when I start plugging in more and more negative values. Well, they're negative values, so I'm going to get a positive there. I'm going to get 1 plus something because it's going to end up being positive. But if you look at 1 over x, the bigger the number is in the denominator, the closer 1 over x gets to 0. So you can even test that out. Because like 1 divided by 20 is 0.05. If you do 1 divided by 2,000, it's 0.0005. The larger the number is that you plug in for x, the closer 1 over x gets to 0. So there's this little thinking trick. And so we're saying when x goes to negative infinity, that becomes 0, or gets close to, it approaches 0, and you have this. Which then is just algebra from here. It's negative 2 times 1 over 1, which is negative 2 times 1, which is negative 2. So one of the videos shows this. It's using some tricks of limits. This is the kind of stuff that you're going to see when you get to calculus. The easiest thing when I see something like this is just to recognize, oh, it's asking for the horizontal asymptote, and then use your rules for finding the horizontal asymptote to find the limit without doing all this complicated algebra. But all this work is if you were to do it algebraically, which involves some thinking, and you have to kind of think through things, and it's a little complicated. So you're not required to show your work that way. You can just say, oh, it's the horizontal asymptote. Here's the horizontal asymptote. This is my limit. Are there any questions? All right, so that was it. I tried to rush at the end. I overplanned. But that's limits in a nutshell. I'm going to keep my other limits videos that I have up so that you can watch those if you want to see some different examples. I might explain it differently in some of those other videos. But that is it. So thank you guys for joining.